So if I were to plug in a 6 here, because my critical numbers are 6, this is my second derivative. Obviously, if I were finding second derivative, I would not leave it like this. I would make it prettier. But if you're just using second derivative test, plug it in before you have to do all the work of simplifying it. Because if I plug in a 6 here, I'm going to get a 0 for this whole group, and I'm going to get a 0 for this whole group. So 0 plus 0, which means there's not a max or min there. And then if I plug in a 12/5, so let's say I plug in 2.4 here, then I am going to get a negative number, actually, is what's actually going to happen, because this is end up negative, and this will be negative as well. So you end up with a negative number here, so it's concave down, which means the 12/5 is actually a maximum. All right. I will also use a 0 too, I believe, because of this guy right here. You'll use a 0 as well, and 0 is going to be a positive. So at 0, it's going to be positive. At 12/5, it's going to be negative, and it is this is actually going to be 0 here. So that tells you 12/5 is concave down, which means this is a max. 6 is 0, so you cannot determine it. You're not going to have a max or a min. No max or min there. And then 0 is actually going to be concave up, because you're going to get a positive, which means it is a minimum.
I was wondering about 0. I was like, take out the x.
So in limits and infinity, we actually have talked about this a little bit when we did pre-calculus. You have to think about what's happening, not that your limit itself is infinity, but what's happening as your x is approaching infinity. And so that's what this is looking at right here. As your x is approaching an infinite or a negative infinite, what is actually happening here? And you can see when they actually plug it into some type of chart that it is, as it's going, they're both going to the same value here, which is 3. And you can see that on the graph as well. And so they actually give us a definition of infinity here. Let L be a real number. The statement that x approaches infinity, f of x equals L, means that for every epsilon greater than 0, there is an m, such that, remember, you're way back when we did the formal definition of limit, all right? For every epsilon, there's a delta. And so they're saying there is going to be a number that y is going to be approaching. And the same thing is true as you approach negative infinity. And you have to keep in mind, now we're no longer talking about infinite limits where y is shooting off to infinity. We're talking about what is happening as x is shooting off to infinity, what's actually going on there. And we actually hit this in pre-calculus when we dealt with horizontal asymptotes, right? And so what's actually created here, if it's shooting off towards infinity, is it's creating a y equals L, L being the limit, which is your horizontal asymptote. So while it gets infinitely close to this, it's never going to actually touch it. However, it is your limit, because that's what is continually approaching as you go. And so the theorem here says if R is a positive rational number and C is a real number, then the limit is C over x of R, and it's defined by when x is less than 0, and you get your negative infinity there as well. So let's look at the example that they've given us. Evaluating a limit. Now, as you evaluate these limits, you have to think what is going on with your denominator for this first example, right? They want the limit as x approaches infinity. So we have this number here approaching infinity. That is not going to affect my 5 at all, right? And so my limit of a constant is not affected by what's happening to x. My limit of a constant is literally just going to be that constant. So now we have to worry about what's my limit doing here. Well, I have a 2 on top, and then my denominator is continually getting bigger and then squared. And so if I have a constant on top and my denominator is continually getting larger, then that means it's going to be a really, really small fraction. And so if you look at that, this fraction is continually getting smaller. 2 over 1 squared, well, 2 over 4 squared, well, 2 over 400 squared, right? And so all of a sudden, we have a ginormous denominator and a numerator that is a constant. And so this guy's approaching what? Small fractions. So if we're approaching, let's see, if we have 2 over 1 squared, that's going to be 2. 2 over 4 squared, that's going to be 2 over 16, right? So we're continually moving towards 0 here, right? And so this is going to be 0. So since my limit does not affect my constant, that's going to be 5. This piece of it is just going to be 0. Our rules of limits say you can just add those limits, and that is going to be what's going on here. So my limit here is just 5. Make sense? Let's look at the next one. So in this case, we have an x on the top and on the bottom. And so this is where we start looking at what's happening at them individually, all right? And so the minus 1 and the plus 1 are really insignificant. I use the example of if you have $1 million and you lose $1 or you add $1, you're not going to notice. But if you have $5 and you add $1 or lose $1, you're going to notice. And so if these x's are both approaching infinity, these guys become insignificant. Really all we're worried about is what's happening here. And those x's are approaching the same number. Infinity obviously being a concept, but if you plug in numbers and make a chart, you're plugging in the same number on top and bottom. And so what actually happens here is the infinity cancels out the infinity. And so my limit here becomes just my 2, because the 1's become insignificant, and whatever number you put in top and on bottom, they're going to end up canceling. You're going to put the top one in, it's going to double, the bottom one does not. You're going to end up with just the 2. And so that's where we move towards what we learned with horizontal asymptotes. We move towards these shortcut type things going on. If you look at example 3 at the top of page 195, then you will see 3 different problems that look almost identical, right? The difference is your degrees. And so this is where our shortcuts come into play. Now, if you'll keep in mind, the shortcuts work here as well. The first one we have a degree of 1 on the top and a degree of 2 on the bottom. That means my denominator is getting infinitely larger than my numerator because it's being doubled. So whatever huge number I put in there, it's actually going to square at the bottom, which means this is going to be the same concept as when I had a constant at the top and a constant at the bottom. When my degree is bigger on the bottom than on the top, this guy right here is going to be approaching 0. And so instead of thinking of asymptotes, we're actually thinking of limit form. And so my limit here is going to be the same thing as what's happening if I were to say what the asymptote is. The limit here then now is going to be 0 because my degree is bigger on bottom than on top. B is just like the example that we just did, all right? The example we just did had the same degree on the top and the bottom, in this case 2 and 2. The 5's become insignificant because they are nothing compared to infinity, right? And then the squareds end up canceling each other out, so we use our coefficients here. Normally we would say, oh, I have a horizontal asymptote at 2/3. That is true. In this case, we're putting it into calculus form, and we're saying my limit here is going to be 2/3. So then that takes us to what happens when I have a higher degree on top than I do on bottom, right? And so in the asymptote world, we would say we don't have one. There's no asymptote. But we're talking about limits here. And so now all of a sudden, we actually have an infinite limit here. And so for this and these purposes, we would say, well, we can't conclude a rational limit, right? So when they're asking for a rational limit, you're going to say it doesn't exist, just like you would for the asymptote. You would say, nope, a rational limit does not exist. However, when we talk about infinite limits, which we're going to do infinite limits in the next section, you would go from here and say, well, I have to decide what it is actually approaching. In this case, you'll see, well, you basically end up with the x's becoming insignificant except for that 1. The 5 and the 1 become insignificant, and I can do my same process here. And so I end up with just a 2x over 3. In this case, my 3 is doing nothing, so my numerator is going to move to infinity, and my denominator is going to stay a 3. A rational limit does not exist here. An infinite limit does. And so you will then start determining, am I approaching positive or am I approaching negative infinity? What's actually happening here? And so as we move into infinite limits later on, you're actually going to not say does not exist here. You're going to give me an infinite limit. If they ask for a rational limit, infinity is not a rational number. It's a concept. So you would say no rational number exists. However, infinite limits do exist. Middle of page 195. These are the guidelines for finding limits at infinity of rational functions. if the degree of the numerator is less than the degree of the denominator, here we go, it's my shortcuts. The limit of the rational function is 0. If the degree of the numerator is equal to, the limit is basically the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. And again, when they say limit does not exist, that is rational limit does not exist. All right? So look at the ones they've given us now. All right? So they've thrown in some radical functions here. The reason they're doing this is because you have to consider your degree when you end up with a rational function. Now, they go through the entire process of actually calculating it. And honestly, what you have to keep in mind is what's actually happening to that variable when they throw the square root in here. And so what's actually happening to the variable is you're taking the square root of the variable. Now, we know that I can't just, in the square root world, just separate them when there's an addition and subtraction. All right? So in the world of actually processing this the way you're supposed to process that, I can't just say, oh, well, that's the square root of 2x squared plus the square root of 1. That's not true mathematically. However, we are now talking about infinity, okay? And so once again, you have to go back to the significance of that addition or subtraction, the significance of it. If I put in a 2 there, well, the significance of the 1 is pretty important because I just have 2 times 2 squared plus 1. All right, that 1's going to make a difference. But if I'm throwing in like 700 there, then 2 times 700 squared plus 1, ignore the 1, not going to be close enough when you take a square root, right? And so normally in the real world, I wouldn't say, oh, well, don't worry about the plus 1 under the root. No, you would. You can only separate them if there's multiplication or division. However, we're talking about limits as x approaches infinity. And so now I have to worry about it. I don't have to worry about it. So now I just have to look at the 3x over the square root of 2x squared. They do the long process. They take out the x squared and they show you what the y's and, but the truth is the reason it doesn't work is you're talking about infinity compared to plus 1. And so it's like the insignificance of, the world compared to an ant on the world. Like we're talking about creation versus an ant. The insignificance is that big when you talk about infinity to plus 1. And so we can ignore it. And so when we do that, then we also have to just say, okay, what happens with an x squared when we square root it? Well, when you square root a square, what happens to it? It becomes just an x. So you end up with just 3x over the square root of 2 times x. That we can do. And that's the same thing that happens. Degree on top and degree on bottom are the same. It doesn't look like they're initially the same, but when you do it that way, they are. And so this becomes your limit. And so it's the same. And so the only thing you have to consider then is the positives and negatives here. So here I'm approaching positive infinity. Over here on the right, I'm approaching negative infinity. And so it actually does matter what you're approaching here at this point, whether it's positive or negative infinity, because it doesn't technically just zero out. 1 actually will become positive. Because if you look at, so if I looked at the ones that didn't have a root in it, then if I had an x over an x squared, it didn't matter if I was approaching positive or negative infinity, right? It just mattered that the 1 was getting bigger and I was approaching 0 either way. When I have a root, then the negative and positive matters. So here I'm approaching positive, and so this guy is going to square and become positive, and that guy is going to stay positive, right? But when I have negative, this guy's going to square, and I'm going to have a positive, which I have to have a root, right? But this guy does not square, and he is going to be a negative number. And so while the infinities will cancel out, the negative piece of it will not, right? And so now for this one, I actually have to consider my positive negative going on here. So in this case, this numerator would stay negative. So I would end up with a negative 3 over the square root of 2 because it actually matters what's happening here. And you can see the graph. So they've given us the graph here, right? And you can see in this graph what actually happens. As I'm approaching positive infinity, I have a positive over a positive. As I'm approaching negative infinity, I have a negative over negative. And what's interesting about horizontal asymptotes is you can jump over them. You see he crosses it. Vertical asymptotes, that's not true. Vertical asymptote, the function is actually undefined there. But with horizontal asymptotes, it's not undefined there. It's saying at some point in that graph, it's going to be approaching that line. It doesn't mean it never touches it, okay? And so in this case, it actually touches it and goes back. And so that's the difference between those types of asymptotes. All right, so let f be a function defined on the interval a to infinity. The statement as x approaches infinity of f of x equals infinity means that for each positive number, it is approaching a positive number. And the statement as x approaches infinity is a negative infinity. Then it means that for each negative number, there's a corresponding number. So basically what happens is when you come up to one and you are going to get does not exist, that is a rational answer as far as rational numbers goes. No, a rational limit does not exist. So then an infinite limit will exist. And you are literally just trying to find out if it is approaching positive or negative infinity. And you will use this using your basic rules of algebra. That's what you're going to do here. And so this is the first one they give us, which this one's really simple. My basic rules of algebra say that if I am putting a positive number into this and I am cubing it, I am going to get a positive number. That's what the rule says. So that means my limit here is going to be positive infinity. My rules of algebra tell me that if I put a negative number in here and I cube it, I'm going to get a negative number. So therefore, my answer here is going to be negative infinity. Just that simple. So when you use these shortcuts and you get an answer that does not exist normally, like for a horizontal asymptote, you flip over and say, okay, a rational does not exist, but an infinite limit does exist. So what would it be, positive or negative infinity? Those are your only options. If it comes up across one that's going to be an infinity, you have a 50-50 chance here, right? You just have to figure out logically what it's going to be. Look at the next example. All right, these are both examples where you would have an infinite limit. Example 8. All right, this first one is approaching positive infinity. So then what happens if it's approaching positive infinity? Well, we're going to see exactly what happens. We're going to say, well, a positive number squared, right, minus a positive number. Well, a huge number, if I square it, is going to be bigger than a huge number multiplied by 4, right? So anything bigger than 4 is going to yield a positive on top. So this is going to be a positive on top, all right? For this next one, the denominator, well, I'm putting a positive number in, I'm adding 1. Well, the denominator is also going to be positive. My rules of algebra tell me if I have a positive divided by a positive, I get a positive. And so my answer here is going to be positive infinity. All right, look at this one. If I put in a negative number and square it, it will be positive. And then if I subtract a negative number, that is adding. So a positive plus a positive is going to give me a positive on top. On bottom, I have a huge negative number and I'm adding 1. That's going to be negative. My rules of algebra tell me if I have a positive divided by a negative, then I have a negative infinity. That is infinite limits. So vertical and horizontal asymptotes are kind of what you're used to. This is an oblique, which means you actually have a linear, like with a slope other than, one undefined or 0. And so it actually approaches, you can see that as x is approaching infinity, this is continually going up. As x approaches negative infinity, it's continually going down. And so you actually end up with now it won't always be oblique. You can think about it this way. Technically a parabola would be infinite limits, correct? I mean, if you had something like this and you had a parabola, is that not approaching infinity as one approaches infinity and infinity as the other approaches infinity, right? Right, and so, yeah, parabolas are always popular in standardized testing. And remember when we did end behavior, right? End behavior is basically just telling you infinite limits. It's going off to infinity one way and infinity the other way. And all of those were just standard polynomials, which would have been an infinite limit because it has no denominator. So this first one's easy. These are just your shortcuts. Your limit here, what's that one?
0.
Yeah, it's 0. Limit here.
3, -2.
Negative 2/3, right? And pay attention to this. They like to throw those into standardized tests, by the way. They like to throw it where it's a secondary and it's a negative. This last one, this would actually be an infinite limit. So a rational limit does not exist. And then you would, when we get to infinite limits in this next little section here, then you would find an infinite limit. So even though originally we said, okay, rational doesn't exist, we have 3 minus this huge number, negative, over a huge number minus 1, positive, so negative infinity.